anything you want there. So, you know, if you come prepared, you can get some very good value for your right lens. Okay then, so this is a linear algebra lecture. So where were we? We're talking about vector spaces and their inner products. And while this is linear algebra, it does have a lot of chimes quite strongly with the subject of Fourier series that we're doing in the analytical methods lecture. So we had, what have we seen so far? We've seen the defining criteria for a inner product, the linearity, symmetry, and positive definiteness conditions. Conditions 1, 2, and 3 on page 29 of Stephen's notes for an inner product. We've seen the way that inner products give rise to norms on the vector space, and a norm being a generalization of the concept of length. Okay, these are these length-like measures that you always have whenever you've got an inner product on the vector space. Even though the objects in the vector space, the vectors, might not have an immediate geometric interpretation, because they might be functions, polynomials, they might be vector spaces of matrices. So even though the elements might not be immediately or explicitly being conceived of as points in space, where you'd have an immediate geometric notion of length, and you still have these length-like concepts called norms, and indeed angles as well. Okay? Cosine of the angle between two vectors can be defined purely in terms of the inner product. In terms of the inner product between the two vectors and the norms, but the norms are defined in terms of the inner product. So norm, the inner product we see then as this underlying structure that's giving rise to the norm and the angle and so on. So what we were doing last week in this topic, we were looking at the concepts of orthogonality and orthonormalness. In general, a pair of vectors are orthogonal with respect to the inner product if the inner product between them is 0. Okay? And you can speak of an orthogonal set of vectors, more than 2 vectors. You can have a bunch of orthogonal vectors. And what you mean by that, what is meant by that, is that the inner product of any 2 different vectors from the set is 0. So they're all mutually orthogonal, all orthogonal to each other within that set. That's what we mean by saying the set of vectors is orthogonal. We have that exact concept in the Fourier series when we say the set of basis functions, the constant function 1, the cosine functions, the sine functions, they are mutually orthogonal. We also met the Kashi-Schwarz inequality, which is a consequence of the defining conditions of an inner product. So all inner products satisfy the Kashi-Schwarz inequality. And we've seen applications of that as a method to give an upper bound on integrals which cannot be performed analytically. The functions you're integrating don't have nice closed forms functions for their integrals. The computer can integrate them numerically, but in the absence of that, we can obtain upper bounds in their value by applying the Cauchy-Schwarz inequality. So moving on then, there's a theorem at the top of page 33, theorem 4.2. And this relates to properties of the basis in a vector space and what the coefficients of a vector with respect to that basis, what they look like. Okay? Now this theorem 4.2, as in a lot of these things that we're looking at here, a lot of them can be seen as generalizations of the much more familiar facts that you already know about from the familiar vector spaces of 2- and 3-dimensional geometric vectors. Okay? So this is a generalization of familiar facts about 2 or 3D vectors and the dot product. The dot product was our first example of an inner product. You can view the concept of an inner product as being generalization of the dot product to whatever the vector space is. Okay. So what's the familiar fact? The familiar fact is, consider the standard basis. So people in maths and graphics unit will be, be able to do this in their sleep. The standard basis in R3 is these three vectors. They're a standard basis. They're the nicest basis you could have. Any vector x from V3R can be expressed as a linear combination of these, alpha 1 E1 plus an alpha 2 E2 plus an alpha 3 E3. And what are these alphas? In terms of the dot product, what are the alphas? In terms of the information on the page? So an expression for what these coefficients alpha are in terms of other stuff on the page. They're the coefficients of the vector x with respect to that standard basis. So they relate to the vector x and the standard basis through the dot product. Okay? The coefficient alpha I is exactly the dot product of x with the corresponding basis. Okay. And facts, the technical explanation behind this comes from the fact that the length of each of these vectors, basis vectors, is 1, and they're all mutually orthogonal. You take the inner product and then take the dot product of any two of them, you get 0. So that's the kind of familiar background, and the statement in theorem 4.2 is really just a generalization of that, an extension of that to the general setting of a vector space with an inner product. Okay, so let's have a look at the statement there. So this set O, it's a bit confusing. Head and tail on it. O is a set of vectors. Many you've got V1 up to Vn from some vector space, and this is an orthogonal set of vectors with respect to the inner product phi an orthogonal basis of vectors. Basis of vectors with respect to the inner product. Yeah. So if you've got a vector v from the space, then of course, because they're a basis, v must be expressible as a linear combination of the basis vectors with some coefficients alpha I. And all theorem 4.2 says is it just states the definition of these coefficients alpha I in terms of the inner product and the vector you're talking about and the basis vectors vi. Okay. And you can prove it is if you take the inner product. Take the inner product of both sides with one of the basis vectors. Okay. So if you take the inner product phi of the left-hand side with the ith basis vector, okay, by definition, this See, the vector v has this expression as a linear combination of the basis vectors. Okay. But now the first defining property of the inner product is that the inner product is linear in the first argument, in the first position. Okay. So in this first position, what do we have except a big linear combination? Okay. So those linear combination operations, the summation and the scalar multiplication, they can all be taken outside the inner product. And phi of this big linear combination is instead the linear combination of the individual, oops, I've done a mistake here. I've done a bad, but I've used vi for the ith basis vector, and so I shouldn't be reused. So I is some particular value. So I shouldn't be using I again for the summation index. So I'm going to change my summation index to j. Change that to j. Okay, because the vi is one of the v's. Okay, so change my summation index to j. So those linear operation, it's not 5, it's an n at the top. Those linear combination operations can be taken outside, and they're multiplying these inner products here, which is the inner product of dj with vi. Okay, but other information in the setup, we said that the basis v1 up to vn is an orthogonal basis with respect to the inner product. So here we are, careless, just flagrantly taking the inner product of the vj with the vi. Okay. Basis vectors with this other one. Okay. But they're not always different, because in the course of summing from j equals 1 up to n, somewhere along the way you're going to hit the value I. And when you do, you're taking the inner product of vi with vi. So that's not 0. That's the square of the norm of vi. Okay? But all the other inner products with a vj with a different vi, those are all 0 because of the orthogonality of the set of vectors. The orthogonality of the vectors v1 to vn. Okay. Go taking the inner product of pairs of them, you're always going to get 0 except when the two vectors are the same. So all of the other terms in the sum don't get hit by a 0 here. 0 times alpha j. So it doesn't contribute anything to the sum. So then this equation you can immediately turn around as alpha I then is the inner product of v with vi divided by the inner product of vi with itself. Okay? So that's exactly the equation in the statement of theorem 4.2, just like a proof of theorem 4.2. So an orthogonal basis, when you look at any vector as a linear combination of those basis vectors, the coefficients that occur are exactly analogous to what happens in the case of, say, using the standard basis and the dot product in the normal familiar Euclidean vector spaces, 2 and 3-dimensional vectors. When viewed in this kind of general setting, these are sometimes called the Fourier coefficients. Fourier coefficients of the vector v with respect to the the VI, the basis VI. Okay, so that's obviously stressing the connection of what's going on in the Fourier series part of the course. Okay, you wouldn't really use these terms if you're talking about the Euclidean vector space, the normal familiar geometric vector space, because it would sound a bit funny there. You're just talking about normal vectors being perpendicular to one another and regular coefficients. But in this more abstract setting of just some general vector space and some inner product, then we can use that term, the Fourier coefficients. Any questions? Anything I could clarify? Okay. So the next section to come in the notes there in the rest of page 33 is Stephen introduces a number of definitions and results about some of these concepts in the context of matrices. Okay? So the setting here, roughly speaking, is the vector space of all matrices of a certain size, okay? All square matrices of a certain size. So I'll just switch back to the notes for a short moment. Now, some of these we've been talking about already in some of the previous in-class exercises. Okay, so you would already be familiar with the idea of a symmetric matrix, a matrix where the entries either side of the main diagonal going from top left to bottom right of the matrix, where the entries are the same either side of the main diagonal. Okay, so that's what we mean by symmetric matrix. It can be interpreted quite nicely in terms of the transpose operations. When you transpose a matrix, you turn the rows into columns and vice versa. Okay? You're essentially reflecting it in its main diagonal. Okay? And so if A is the same, if performing that transpose operation does not change the matrix A, that's equivalent to it being a symmetric matrix. So these theorems here record a number of important facts that we know about symmetric matrices. For instance, the eigenvalues that are associated to a symmetric matrix are always real numbers. Okay? So this is significant because you're familiar with the idea that the eigenvalues come about as the zeros of the characteristic equation of the matrix. You take the determinant of A minus lambda I times the identity matrix. Okay, it gives you a polynomial in the variable lambda, and you're finding the roots of that to give the eigenvalues. But you're also familiar with the fact that polynomials don't necessarily have a full complement of real roots. Sometimes they have imaginary roots as well. If they fail to have real roots, they will always have a full complement. You count them up to multiplicity. They will have a full complement of roots, but some of them might be complex. And in general, if you're just given a random matrix, you might expect some of its eigenvalues to be complex. That's the kind of typical picture. Okay? But to make when you know the matrix is symmetric, it's really knowing a lot about its structure. And in those cases, we know that the eigenvalues are all real. And secondly, in theorem 4.3 there, we know that if you look at eigenvectors corresponding to different eigenvalues, they will be orthogonal to one another. Now that's a stronger condition than what we know in general. In general, for a general matrix which you don't know to be symmetric, if you look at different eigenvalues, then the eigenvectors corresponding to those eigenvalues will be not necessarily orthogonal to the other ones, but they will be linearly independent of the other ones. Okay? So that's something that we know about eigenvectors or eigenspaces in general. Okay? The eigenspaces corresponding to different eigenvalues are linearly independent of one another. But for symmetric matrices, again, things are a bit nicer, a bit more well understood, a bit more straighter, a bit more lined up. The eigenvectors corresponding to different eigenvalues are actually orthogonal to one another. Right angles to one another. So that means because our symmetric matrix always has real eigenvalues, It's always going to have a full complement of eigenvalues, and they'll always be diagonalizable matrices. You can always bring them to be diagonal matrices, where the entries in the main diagonal and everything in the off diagonal will be 0. That's what a diagonal matrix is. The entries along the main diagonal will be the eigenvalues. Okay? Some of them may be repeated, of course, because sometimes the eigenvalues have they are multiplicity greater than 1. Okay. Then we have this definition, the concept of an orthogonal matrix. You see, this transformation matrix P appearing here, normally this is P inverse AP. But the one that appears for the case of a symmetric matrix is kind of special. That still is P inverse in the first position there, but it can also be represented as P transpose. Okay. So those matrices where P transpose is the same as P inverse of P, these are called orthogonal matrices. Okay. And we had that definition, we considered that definition a few lectures ago when we were doing some of the earlier class exercises. A lot is known about orthogonal matrices as well. In particular, the equivalent concept in linear transformations. You see, remember, matrices, what are matrices? Well, one strong interpretation of explaining what a matrix really is, okay, it's a square of numbers, but really it's representing a linear transformation from the vector space that size to itself. So a matrix is orthogonal, but if you consider the linear transformation represented by an orthogonal matrix, it has a very special property, which is expressed here algebraically in terms of the inner product. It says if you take the inner product of T applied to U with T applied to V, it's always the same as the inner product of just U with V. So in other words, applying a linear transformation which comes from an orthogonal matrix, this does not affect the inner product values. A pair of vectors U and V have a certain inner product, and when you transform them by the linear transformation T, which comes from an orthogonal matrix, the new inner product value will be exactly the same as the previous one. So this has a geometric interpretation. Because it's leaving the inner product unchanged, these geometric concepts of lengths or norms and angles, these come from the inner product values. These are defined in terms of the inner product. So such a matrix, or such a transformation, a linear transformation represented by an orthogonal matrix, this will be one that preserves norms and angles. Doesn't change, okay? Because it's not changing the underlying inner product values. Okay? So these are examples of results that come, when you're studying these inner products and the properties they have, and you can kind of see how it's tying up together a lot of algebraic concepts and a lot of geometric concepts. Okay? So in this more abstract setting, you really see, more and more evidence of how, all the connections there are in mathematics. Okay? So these very strong geometric concepts of length-like things and angle-like things and perpendicular-like concepts, and they're all combined together and all represented very strongly in the algebraic side. Okay. Now, following on from that, in the next couple of pages, things get a bit more practical and kind of task-oriented again. Okay. So that's in this concept of projections. So from your study of two and three dimensional vector spaces, and again, people in computer graphics will be very familiar with this thing. We have the whole notion of things can be perpendicular to one another, and we can also project vectors onto other vectors, and we project vectors onto planes. Okay? Well, these concepts can be generalized to the setting of any vector space which has an inner product. Okay? Because we've seen how the inner product gives rise to a length-like thing called a norm, and you can define cosines of angles as well. Okay. So following the definition, following what we know about regular geometric vectors and dot product, how to talk about projections there, we can define what it means to talk about projection in a more general sense. Okay? As long as we're in a vector space which has an inner product, we can talk about projections like this. And this agrees when you take this description and replace the vector space with the familiar 2 or 3 dimensional Euclidean vector space, and replace the inner product with the dot product, then it becomes exactly the familiar facts you already know, the familiar geometric relations you already know between 2 and 3 dimensional vectors and the dot product. Okay? But this is its more general description. Okay? So if you have a pair of vectors u and v, you can speak, okay, typically these will be pointing in different directions. Okay? If you choose a random vector u and a random vector v from your vector space, you'd be lucky to find them both pointing in the same direction. So typically they'll have different directions. But we can talk about the projection of u onto v. Okay, so schematically, visually, we would represent this as, well, here's a vector v, here's u. But this vector here, which follows along v, which follows along the vector v, until you find that the line joining u and this portion that's partway along v, until you find that the line joining those 2 points is orthogonal to the vector v. Okay? And we talk about this as being the projection of u onto v, or the orthogonal projection of the vector u onto the vector v. It's a vector pointing in the same direction of v, so it's some scalar multiple of the vector v. So the cv here is a scalar multiple, the scalar c multiplied by the vector v. And the value of that scalar, well, it's exactly the kind of Fourier coefficient of u with respect to the vector v. It's the same ratio of inner product values that came up in the theorem that we just proved. Okay? So the coefficient c, which gives you the scalar multiple of the vector v, which is the projection of the vector u onto v, this is exactly this ratio here. Phi of u with v, the inner product of u with v, rescaled by the inner product of v with itself, which geometrically you think that thing in the denominator is the square of the norm of the vector v. Okay, so that ratio is the projection of the vector u onto v. Okay, it also generalizes, so this second diagram here, which kind of appears to show a plane W, and appears to show the projection of a vector u onto the plane W. But actually, you see, we've only got 2 or, at most 3 dimensions in which we can draw our diagrams, in which our brains can kind of visually interpret a diagram. For this kind of diagram, you commonly come across these kind of diagrams where, although that looks like a plane, in general, that might represent any vector subspace of the containing vector space. Okay? So that this subspace W contains the origins, it's got 0 written on it. That vector subspace W may have more dimensions than 2. It may be a kind of high dimensional thing, maybe inside a high dimensional vector space. And this vector U is supposed to be some vector outside of the vector subspace W. But we can still talk about projecting U onto the vector subspace W. And so that diagram there, B, is associated to the statement of theorem 4.6 here. Okay. So suppose you've got some set of basis vectors, W up to WR. We'll suppose that they're a nice enough basis for the vector subspace capital W. We'll suppose they're an orthogonal set of vectors. Okay. So you can think of that W, think of that set of little w's, W1 up to WR, as being a subspace, as being a basis for this vector subspace W. Okay. So W, capital W, the vector subspace W, has as an orthogonal basis this set of little w vectors. Then you can define this. You can define this vector here, U prime, which is the vector U itself minus. Well, so what's this combination here? This combination here, the summation of the basis vectors little w, using these coefficients Ci. Now, if you choose as the coefficient Ci, if you choose the Fourier coefficients of U with respect to the basis vector Wy, then actually this linear combination here will be exactly the projection of the vector u onto the vector subspace capital W. Okay? So the statement, okay, this is bundled up in the form of a theorem statement. The statement that it's saying here is that u prime is orthogonal to every one of the little w's. U prime is the difference between u and this summation here. So if you go back to the diagram B, what u prime is there is u prime is this vertical looking vector here, coming out of the vector subspace W and pointing to the tip of u. Okay, so that's u minus, well, it's already written there. Notice I've forgotten it's already written there. It's u minus the projection of u onto the vector subspace W. And this vector, well, what the theorem is saying is that this vector here will always be at a right hand, or will always be orthogonal to the vector subspace W. Okay. Again, this is just the generalization of things you already know about standard geometric vectors and the dot product. Okay. Now that brings us on to what's called the Gram-Schmidt orthogonalization process. So what's at issue here is, in general, we prefer our bases to be, well, like the standard basis. The standard basis for 2 or 3 dimensions, these nice basis vectors that are all perpendicular to one another, and they're all standardized in the sense that they all have length 1. Okay? These unit vectors that point along the x, y, and z axis. Okay? They're a nice, well-behaved basis for whether we're talking about 2 or 3 dimensional space. So in general, it's easier, or conceptually easier, and in terms of calculations, it's often easier if the basis that we're working with, whether it be for the whole vector space, whatever that is, or some interesting subspace of it. In general, we prefer them to be what are called orthonormal. Orthonormal. Okay. Orthonormal means orthogonal to one another, mutually orthogonal. Now, orthogonal with respect to whatever the inner product is. Okay? That always is. That's the definition of orthogonal. So orthogonal to one another, and all of norm 1. Or length 1. Okay? All of norm 1. Just like the standard basis in 2 or 3 dimensions. Okay? So what the Gram-Schmidt orthogonalization process is, as the name suggests, it's an algorithm for taking a general basis, an arbitrary basis for a space, which might not consist of orthogonal vectors. Remember, a basis has to consist of linearly independent vectors. That's a lot weaker than saying they're all orthogonal to one another. So the Gram-Schmidt orthogonalization process is some algorithm that takes an arbitrary basis and works on it. Okay, straightens it out, and standardizes it so that it is an orthonormal basis. Okay? Something that straightens out and standardizes the basis. Now it might go around and it might be altering the individual basis vectors that you're starting off with. But what it won't alter is the vector subspace spanned by those vectors. Remember, vector spaces can have many different bases. Bases are by no means unique. But whatever basis we start out with, when we apply this process to it, it's going to straighten out. Well, straighten out, I mean, make everything orthogonal to one another, and standardize, meaning it's going to produce everything of length 1, norm 1, but still for the same space. So straightens out and standardizes the basis for this space. And if you look at the statement of it, so the algorithm is described here as a sequence of or as a kind of recipe how to produce the new basis. So these vectors vi here, the subject of all these equations, the vi is the new basis. Okay. The vectors ui, which appear here in the equations, they're the old basis. Okay. So suppose you have a basis u1 to un for some space. And what the orthogonalization process does is, well, the orthogonalization process produces a new set of vectors, the new set of vectors v1 to vn. The property that they'll have when they come out of this process is that the v's will all be orthogonal to one another. You take the inner product of any v with any other v, you're going to get 0. It doesn't do the standardization step. We have to do that afterwards. So afterwards, we can go back and check each of the new basis vectors vi, take their norms, see how long they are, and rescale it if necessary by the reciprocal of the norm to standardize them down to length 1. Okay. And so if you do those two operations, straightening them out using these equations and then renormalizing them, you'll end up with an orthonormal basis for the same space V. Now, if you look at the structure of the equations feature, well, okay, u1 is just the same as v1. So you just choose a vector to start with, and you name that as the first basis vector. But then the second vector v2 that you produce is you produce u2 minus the projection of u2 onto v1. Okay, this is the Fourier coefficient of u2 with respect to v1. And we're subtracting that Fourier coefficient times v1. Okay. If you go back to your diagrams here, supposing u and v are the two vectors you're starting with. Well, we choose v and we keep that as our first basis vector. But then instead of keeping u as our second basis vector, we take this object, u minus the projection of u onto v. We take this vector as the second basis vector. Okay? So it's not the original second basis vector u, but it's this new one, which by construction, because we've removed the projection of u onto v, we've made it orthogonal to v. Okay? So you can see that this is suggested by the picture, it's a right angle, but in terms of what you've done with the unit product, is you produce this second vector u minus cv, which is going to be orthogonal to v. But still span the two of them, v and u minus cv, are still going to span the same space spanned by u and v. And then, as you can see, it continues as an iterative procedure. The new v3 will be the old v3 minus the projection of u3 onto v1 and u3 onto v2. So that will produce a new vector that is going to be orthogonal to both v1 and v2. You keep repeating this process. At the end of this process, you'll have a collection of vectors v1 up to vn, which will be a basis for the same space, but they'll be orthogonal to one another. And then you can check each one to see what its magnitude is and rescale it if necessary to produce one of length 1. Okay? So let's see an example of this being applied. So we'll take this first example. Here. Okay, so we're starting off with what in some ways you might think is the kind of the most obvious or clearly understandable basis for all polynomials of degree less than or equal to 3. Okay. Considering these as polynomials of degree 3 defined on the interval minus 1 to 1. Okay, so we're considering the vector space of polynomial functions of degree at most 3 defined on the interval minus 1 to 1. This is a vector space. These functions can be added and scalar multiplied to give functions of the same type, polynomial functions, degree at most 3, defined in this interval. There's a clear standard inner product. Standard inner product is phi of fg. Two such polynomials, you integrate the product of them from minus 1 to 1. F of t, g of t dt. You integrate the product of the two polynomials. But the point is, though, although this basis is very easy to understand and appreciate why it's a basis, so you've got each each term from t to the 0, t to the 1, t to the 2, t to the 3. But when you investigate it with respect to this inner product, you find that it isn't actually orthogonal. Okay? Those different polynomial functions are not orthogonal to one. You can appreciate how you can kind of appreciate clearly that they're linearly independent, but they're not really that nice as a basis in the terms of what we've been discussing. They're not orthogonal and they're not normal vectors. Okay, so we can apply the GS process, the Gram-Schmidt orthogonalization process. Okay, we get a new first basis polynomial, which is just equal to the first basis polynomial that we started with. So V1 is the constant polynomial 1. V2 is what V1 was. And then we subtract the projection of V1, sorry, U1, which is the same as V1. We subtract the projection of U2 onto V1. Well, V1 is the same as U1. Okay, so this is the inner product formula, and we're subtracting that multiple of V1. So in this context, what that means is we're taking the constant 1, and we're subtracting the integral from minus 1 to 1, the product of U2 with V1. So U2 is t, V1 is just the constant 1, so we're just subtracting the integral of t dt. I'm dividing this by the integral, by the inner product of V1 itself, which is just the integral from minus 1 to 1 dt, 1 squared. And we're taking this multiple of this multiple of the new basis vector of the old basis vector V1, which is just the constant 1. So when you perform these integrals, so the integral on the top is, of course, is t squared over 2, evaluated at minus 1 and 1. And the integral on the bottom, well, you're just integrating 1, so the integral on the bottom is going to be 2. And when you perform this integral on the top, you've got 1, or you've got a half minus a half again, okay, because you're squaring minus 1 over 2. So you're going to get a numerator of 0 there, which so that's V2. Sorry. This vector, sorry, excuse me, this first vector is V2. So this thing here is in T, excuse me, T. And so this multiple of the constant 1 comes to 0, so it's got a 0 numerator. So we again get the same polynomial T. So the V1 and the V2 happen to be the same as the first two that were in the original basis. But it's thereafter you start to see things change. Okay? So the new basis vector V3 is going to be the old the old basis vector v3, which was t squared. And then we're going to subtract its projections onto both v1 and v2, two new basis vectors that we're working with. Okay? So the projection of t squared onto the constant 1 is just the integral of t squared dt, integral from -1 to 1. We're dividing that by the norm squared of 1, the integral squared of t, so this is 1. And then you're also subtracting the projection of t squared onto v2, this will be the integral of t cubed, because you're integrating t squared times v2, which is t. And then and the denominator here is going the inner product of v2 with itself. So that's going to be the integral of t squared from -1 to 1 dt. And this is all multiplying the old second basis polynomial, which is just t. Okay, when you evaluate these integrals, it comes out as t squared minus 1/3. Okay, this integral is going to give you 0, whereas over here we're going to get 1/3 from this. So this is the second polynomial, and you'll need to continue this process. Okay, as you can see in the example, continuing. The final basis vector, the fourth one, which has to involve a cube. But when you apply the Gram-Schmidt, you get t cubed minus 3t over 5. So actually, to straighten out these polynomials and make them orthogonal to one another, but still have a basis for the same space, i.e. the space of all polynomials, it's actually can sometimes be more convenient to use a basis formed out of these vectors. So the constant polynomial 1, polynomial t squared minus 1/3, and t cubed minus 3t over 5. Okay. So then finally, we would like to then normalize them as well. Normalize them meaning rescaling them by scalars by the reciprocals of their magnitude. So you turn them into vectors with magnitude 1. Okay. But we'll come to the end of the time there. But we'll talk about this more next week. Next week we'll be doing 2 sessions on linear algebra. So I'll finish off that example and do some more examples and also look at some past exam questions. Because if you look at the past exam questions, you'll notice Stephen does like asking a question based on this procedure. It's come up many times before, so we'll have a look at some of those. Yeah.